Is it time to start doing something with these quantum mechanical principles? It's one thing to say, okay, force equals the first derivative of momentum with respect to time, which is F equals ma, Newton's equations, or to bring the first postulate of quantum mechanics, which is the time independent uh, Schrodinger equation. But what about applying these to something? What's the use of it if you can't come up with some answers on physical systems? Because after all, it is physics. Well, in this video, the goal is to get to the hydrogen atom and explain why the hydrogen atom has these discrete frequencies that are seen. So we want to explain the observables. That's where I'm going. But in order to get there, we don't want to start with the most complicated format to get to these things. So here's what I'm going to do. And this is not a unique approach. This is standard on the books. So I'm just going to follow what the standard way is. And the first thing is, what about a free particle? What is the result? How do I solve a free particle? You might think, well, let's say a free particle doesn't have any potential energy, which means there's no forces acting on it. In the Newtonian world, that would just mean a free particle would stay wherever it is. If it's moving, it'll stay moving. If it's stopped, in other words, it's the law of inertia. You'd have no unbalanced forces acting on it. But in the quantum world, let's see if that's really true. Then the next step is to go to a particle. Now, in the text, they say particle in a box. What I would rather say is particle in a tube. We want a tube that's a fixed length and see what the particle does inside of there. Does it bang up on each end of the tube and keep moving, or what's happening? Because it's not a free particle anymore. It's in a little tube. Then the next thing is, let's talk about a spring system or a harmonic oscillator. And to keep the oscillator easy to talk about, I'm going to use math, and we'll just relate it to something that's on an air track. Gravity's not affecting it. And this is a little experiment that would be done with the regular macro or Newtonian mechanics. It's a object on a spring that's going back and forth. Now, if the spring is an ideal spring and the air track is an ideal air track so that the gravity is eliminated, this thing will, once it's pulled up here and let go, that will keep springing back and forth, back and forth, back and forth indefinitely. And then what's next? Well, this next one I'm not real comfortable with, but I'm going to go ahead and do it because it acts as a good introduction to finally the hydrogen atom, where you have a electron that ends up, instead of just driving into the proton, it spins around the proton. And that is it's like rod rotating, a rod rotating. Or, in other words, it's two masses that are tied together somehow and they rotate, or two particles rotating. So, finally, we get to the hydrogen atom, and the little math stuff that we developed up along the way can then be used to apply to the hydrogen atom. Maybe this will have to get broken up into more than one video, but I'll keep going that way. And of course, you can always fast forward a long video if you want to get to the very end and look at the hydrogen atom first. But let's see if this works properly. Let me start by pointing out some things that if you don't have this information, or doesn't make sense to you, then you need to go back and look at some other videos. The primary postulate of quantum mechanics, according to Schrodinger's picture, is this thing right here. And Schrodinger came up with this idea because he postulated, remember it's a postulate, he postulated that this was the general form of the wave equation. General form with de Broglie gives us this momentum in the x direction times x. Now notice I'm only using the x dimension. So if you're okay with that information, let me direct your eye to this. I'm going to call this picture a free wave packet. A free wave packet means that it has both particle and wave duality. For right now, let's just think of it as an electron. An electron that can only move in the x dimension. Free wave packet in one dimension. And for that, we use the variable x. If that's the case, and it's a free wave packet, then that means there are no forces acting on it. If there are no forces acting on it, then it has no potential energy. So let's think of it this way. This is like Newton's first law says that if it's in motion, it's going to remain in motion in this x dimension, either going right or left. Can go right or left. And notice the ends of these tubes are open, or this tube is open. So it can go this way to infinity or that way to infinity. So how does that relate to anything? Well, if it's moving, has a certain momentum, then it's going to continue with that momentum. So what's our approach going to be here? Well, our approach is going to say that the potential energy then is not there. So I'm going to call the potential energy zero. If the potential energy is zero, then that means this whole term goes away. That whole term goes away. So what I'm going to do to emphasize that is I'm going to put a strike through that. So the equation that we have is just this form right here. So I can call that the second partial of our wave function with respect to x equals, now watch what I do. I'm going to multiply both sides by this reciprocal of this ratio, which will eliminate it on the left-hand side. So what I'm going to do is say that that is E times negative 2m over h bar squared times that function. Now look at that and see if you can see if you can convince yourself to go from this step to this step. Notice how much it's simplified. It makes that differential equation very simple. And why should it be that way? Well, we're taking out potential energy, which it's not a very interesting problem if there's no potential energy. Not much going on, but it kind of sets the stage for some other things that we're going to do. Here we are with this relationship. How can we figure out what the energy is, though? What we want to do is find out what the energy is. So let me take the second partial of psi with respect to x, which is, I'm just going to take this equation here and perform that. Now remember, when you take the derivative of an exponential like this, you get that exponential back times the derivative of the power. So the derivative is just going to be this constant I over h bar px. And this one, because it has no x in it, that's just going to be 0. So if we take the second derivative, we'll be performing that operation twice. And here's the way that's going to come out. I'm going to copy the exponential because that's what happens each time. I'm going to copy the exponential. I over h bar times momentum in the x direction times the x position minus e t, and then that's going to be multiplied by this constant twice. I over h bar p x, p in the x dimension, because the first derivative of px times x just gives us px, the constant that's left over. And then I'll have one more of those for the second partial, which is I over h bar p in the x dimension. To simplify this, I can just say that this is the psi function times I is going to be -1. So that's going to be negative px squared over h bar squared. Okay, now let's examine this. This is we're taking each one of these is the second partial of psi with respect to x squared. So whatever we come up with, I should be able to set them equal to one another. So if that's true, then E times -2m over h bar squared would also have to equal minus p sub x squared over h bar squared. Okay, simplifying a little bit so we can examine these things. If you'll notice, this means that if all this looks the same, then I can factor out the psi and just look at these things. So I can look at energy times 2m over h bar squared times negative px squared over h bar squared. So let me see if you buy the next thing that I put in here. I'm going to say that energy equals px squared let's see, that's negative px squared over h bar squared. And then I'm multiplying both sides by this reciprocal to give me minus h bar squared over 2m. Go to the red marker. Negatives go away. H bar squared goes away. So that means that the energy, by solving this free particle, is equal to momentum in the x dimension. So since this is a single dimensional idea, over 2m. What about that? That says that the energy is just like the Newtonian picture. Energy is for a free particle only. For a free particle, it's just momentum squared over 2m's. And since we have no potential energy, what is this? This is just Newtonian kinetic energy. That means that for any momentum, it doesn't have to be a particular kind of momentum. Any momentum value that we come up with is going to give us an energy. Any momentum value and mass of this thing, so it'd be the mass of an electron. That electron can have any energy level in the world depending on what its momentum is. There are no quantum steps. Now, in the future problems, we're going to find out that there are quantum steps and there's only certain energies that are allowed. And that's what's going to happen when we get to the hydrogen atom. But before we get there, we have to go through some little baby steps. That example was boring, but it was easy. It was easy. If p squared over 2m is kinetic energy and you just latch onto that and say that's good. Now, let's take a case where it's a free particle. When it's a free particle in an area, then the potential energy is zero. But we're going to limit it to a space. We're going to put ends on those, or put a barrier on that tube. So that tube does stretch out to infinity, but the particle is inside these two barriers. So that means the potential energy inside is zero. But if we move it outside that barrier, the potential energy is infinite. In other words, it has a potential to have this kinetic energy inside that barrier. So we're going to work with those ideas. And the result that we hope for is that there's something to do with quantum mechanical step functions. Not step functions, but quantum steps or quantum numbers, or the ideas of the energies not being continuous. So here we go with my drawing board once again. Top of the screen is my crude drawing of a tube. This tube that this is in, and this is the x dimension. We only have to deal with one dimension. And instead of a particle, I'm going to put this little wave packet here. And this wave packet can be either stationary, or we'll find out that it can't be stationary. Anyway, depending on the energy levels, this wave packet is going to bang up against the sides of this barrier. This barrier, what I've represented as distance 0, or the origin, and distance a. Just as we can use that in our calculations. So think of this thing as a little ball that's going back and forth and hitting this. Each time it has kinetic energy and it bangs up against the wall and then shifts kinetic energy back in the reverse direction. Now, right at the instant that it hits the wall, the kinetic energy is gone for just this really brief instant. And during that instant, there's a potential for a new kinetic energy. Now you could say, oh, well, it's the Vx would, or potential energy, would equal the kinetic energy in the reverse direction. That's one way to think about it. In other words, you got kinetic energy, potential energy, and then it turns into kinetic energy going the other direction. But we don't know how much energy this thing has. So the potential energy could be any energy, That's why this infinity is down here. At 0 point, it's got infinity. At A, it's got infinity. Don't get hung up on this. We won't really deal with this infinity thing much. We just have to consider the bounds of where the potential energy is zero. It is zero when the x dimension is greater than zero and less than A. Not equal to A, not equal to zero, but this relationship. Now, in order for this thing to actually occur or to make sense, we have to put this wave packet as in super small atomic dimensions. So this A dimension would have to be 1 to 2 times the wave packet size. So if we have an electron, which is really small, obviously, and it's really hard to measure, in fact, maybe impossible to measure the exact dimensions of it, then I'm just calling it this way. That way it can make some of this become a little bit more realistic to you. Now, what did I have this thing up here for? I have the function x and t of this psi function or state function as equal to e to the I over h bar momentum in the x direction times x minus et, which is what Schrodinger used to actually come up with this form of his equation. He assumed this and then came up with this. But this Schrodinger equation is going to be used to find a solution of psi, but it doesn't have to be in this form. So we really don't have to start this way. And in fact, we shouldn't start this way because that will force us into a box that we don't want to be forced into. I don't know any other way to say it. Schrodinger equation, and I'm going to do some stuff here that I hope there's enough steps here to make sense of it. IH bar times negative I omega. This is from the general form of the Schrodinger equation. And then the negative h bar squared over 2m, because negative k squared, so we have h bar omega, which really is the same as h times f. So this is the energy right here. And that energy is also equal to k squared h bar squared over 2m. Now this looks very close to p squared over 2m. So I hope you buy this pretty well at this point so we don't get bogged down. Okay, now I'm going to figure out what is the psi function. I hate saying that word or using that name for the letter psi. But anyway, I wish I had a better letter, but that's the way most of them do it, so why be different? I'm going to make a guess, and that guess is based on a couple things. The psi function has to be zero here. Has to be zero when we're at this zero boundary. Let me get the pointer so you can figure out what I'm doing here. This zero boundary, psi has to be zero. The A boundary, psi has to be zero. Well, there's a function that can be zero at two different points. And since I want to stick with waves, what's the simplest wave equation? The sine wave. So let's try this sine wave out here. I'm going to pick my function for the x as a times sine of sine of x. This is the x thing. And I'm going to put a constant in front of that x. And just so we don't lose sight of it, that there is some time-dependent stuff going on here, e to the negative omega e to the negative I omega t. Now, I'm going to be taking the second derivative of this thing, not the first derivative, because I don't want to worry about the time thing. Let me go back to the canvas here. So I'm not worried about the time part of this. So what I'm going to do is come up here and strike out that part of it. And just make it a function of x and not worry about the time dependence, because I really don't need that for this free particle that's floating around in there. So what can I do to this k? What can I do to the k? What value of the angle that sine is taking that's 0? Well, sine of 0 is 0. Where's the next time that the sine function becomes 0? Sine of pi becomes 0. So let me go ahead and see if you buy this. A times sine of n, where n is an integer, pi over a. So whenever the x value reaches a, it's going to turn into a pi value. 1 pi, 2 pi, 3 pi, 4 pi, so on and so on and so on. If n happens to be 0, well, n is 0. I don't know that we're ever going to have that. I think we'll find out that there is no such thing as n equals 0 for this psi function. So let me finish up here. I'm still in blue, so I'm going to say x. Now, just to convince you that I'm not crazy, I'm going to take the first derivative with respect to x. And this is just to fill in if you forgot this stuff, is going to be the constant, because the derivative rate of change of the constant isn't going to change. And the derivative of the sine is the cosine. Times the derivative of the angle. So the derivative of the angle is, what is it? It's n, let's see, n pi over a. And the second derivative. Trying to go quickly here so I don't lose your attention. And by the way, this video is going to take more than one to get to the hydrogen atom, so don't lose your train of thought. Keep looking up the video. The next video is going to be about a harmonic oscillator. Now, derivative of the cosine is negative sine. So I'm going to put a negative a sine n pi over a x times, and this will be one more of these multiplied, so that's going to be n squared pi squared over a squared. How can we do this? Well, what did I do with k? K was n pi over a. So now this is k squared. So I can take this value and plug it into that value. Change to blue, trying to keep the momentum going on this thing. So the energy, how about let's just put energy, because h bar omega is equal to energy. That the energy is going to be, let's plug in for the k squared. I'll put it in parentheses so you don't lose sight of it. N squared pi squared over a squared. All that was over the denominator, h bar squared. Let me put little parentheses around that so you don't lose. Here's the k squared value over 2m. Let's simplify this thing and see if it all plays out correctly. Okay, let me simplify this. Let me put this as n squared pi squared over, don't forget about the h bar squared over, let's see what ends up in the denominator, a squared 2m. Now, h bar squared is 2 pi over 2 pi squared, so the pi squared is going to disappear. But in the denominator, I'm going to have 4. So that 4 is going to come down here and multiply because it's in the denominator. That is going to end up in this denominator. So that's going to put an 8 down there. So let's keep going. Remember, n is an integer. What does that leave us with? Energy can be any one of the following values, where n is 1, 2, 3, so on. And that means that the lowest energy that we can come up with is n equals 1. So this particle up here is always moving, which if it's a wave packet, that's not too hard to believe. That wave packet confined to this area is going to have quantum energies. Only these quantum energies are allowed. So this was the whole point of doing this thing, was to find out the quantum energies that were allowed. Now, as far as any kind of amplitude of that sine function, I'm going to leave that for another thing because we want to keep up our momentum. We want to go on to the harmonic oscillator. Gee whiz, thanks for watching. What I want to do next is go on to the harmonic oscillator. And please go on to that because these videos get a little long, but I try to keep the momentum going, like I said, and make them fun. So see you on the other side with the harmonic oscillator.